Alright, this is the file number 23, which we started off with a compound energy formalism. The first part I talked about it on an alloy system. And I started yesterday talking about applying the compound energy formalism to ceramic systems, in which you end up having these charged hypothetical compounds. And I talked about a spinel, the 2,3 spinel structure. So on the 2,3 spinel structure you have tetrahedral sites and you have octahedral sites. These are two distinct sublattices with different oxygen coordinations, and then you have O4 here. And as usual, there should be a 2 here. This is the second, this sublattice has one site on it, this sublattice here has 2 sites on it, so there should be a 2. Now, if all the A2 pluses, I don't like this blue stuff. An A2 plus, B3 plus 2O4, that's called a normal spinel, with the 2 pluses here and the 3 pluses on this side. Or the other extreme is a B3 plus, A2 plus, B3 plus 2O4, which is called an inverse spinel. With these, the trivalent ones prefer the tetrahedral sites. Most spinels are mixed spinels, in which you'll have some 2 plus and 3 plus on both sides. And there's a site inversion energy, which tells you which way you want to go. Some ions now, some elements only have one oxidation state. For example, if you're talking about magnesium, you don't have any particular magnesium 3 plus, so the magnesium would only be magnesium 2 plus. Aluminum is only 3 plus. But other elements like iron will have both 2 plus and 3 plus. So even if you've only got one element, you have A2 plus and A3 plus, which can go on both sides. Okay, so to treat this with the compound energy formalism, it says you would expect the Y's are the site fractions, and you have for every Gij as the end member gives energies, 1 for each ion pair. So there'd be A2 plus 2O4, A2 plus A3 plus 2O4. Some of these are charged, some are neutral. So if you have 4 elements, 4 ions here and 4 ions here, you got 16. It's the normal thing, you have 16 end members, some of which are neutral, some of which are charged, and so on. The configurational entropy is in the simple model. You have a random mixing of these ions on their sites, and you have a random mixing of these ions on their sites, the 2 here, because there's supposed to be a 2 down here. And then you have these second nearest neighbor pair energies as well. That's the alpha functions, which come from the edges of the reciprocal system, and these are second nearest neighbor, which in this case means second nearest neighbor. You're talking about, we're ignoring the oxygen lattice, so first nearest neighbors are this sublattice and this sublattice in this context. Actually, if you consider the oxygen, I mean the first nearest neighbors are cation and oxygen. We're forgetting the oxygen, so we're talking just about these 2 sublattices. So by nearest neighbors between 2 sublattices, these are the Gigs. The Gigs, the end members, are really the energies of a pair where you have this on one cationic sublattice and this on another cationic sublattice. There is, of course, an oxygen in between them, but this is what I would mean by a first nearest neighbor pair. A second nearest neighbor pair would be between 2 ions on the same sublattice, and we can add these energies in as well. The main parameters of the formalism, though, are these Gigs. These L's are secondary, as they are in all of these reciprocal systems. Okay, so now these Gigs, as I said, are the formalism parameters, but I mean most of them don't have any physical meaning by themselves. You have to distinguish these from the model parameters. Okay, so the Gigs are the formalism parameters. Some may be equal to Gibbs energies of real compounds. In other cases, certain linear combinations of them have physical significance, and these are the model parameters. So there's a whole, I'm not going to go into all the details here, because I'm just trying to give you the idea of what it's about. We have a number of papers on this, one on homemade spinels by myself and Sergei Dektorov. If you're into this, you might want to read it. But we have the 4 end members. So let's look at Fe3O4 spinel. This is a spinel. It's a mixed spinel, so the iron 2 plus and 3 plus can go on both sites. You have 4 end member Gibbs energies, Fe2 plus, 2 plus, so on. GFE2 plus Fe3 plus is the Gibbs energy of hypothetical normal Fe3O4 with all the 2 plus here and the 3 plus here. Okay. I is a model parameter which is given by this difference, and this is related to the degree of inversion, how far it's inverted towards between the normal and the inverse. There's a model parameter related to the reciprocal exchange of nearest neighbor pairs. Okay. Okay, and some of these, as I showed you yesterday, can be arbitrarily set to 0, and it's these are the only parameters that really influence the distribution and the energy. These are the only ones. Some of them, then generally there are fewer model parameters than there are formalism parameters, which means that some of the formalism parameters are basically arbitrary and the others can be set. You have to be careful as to what you mean by the model parameters are the only ones that have physical significance. You can't just go and set formalism parameters equal to whatever you want. I'll give you an example on the next page. Overly simplified as usual, but this is a mixed spinel AB2O4. So let's say we have a mixed spinel AB2O4. And we're trying to find out the degree of inversion of this spinel. So this could be MgAl2O4, or A and B could be iron plus 2 plus. I'll get the mixed spinel AB2O4. So we have assume that A is only 2 plus and B is only 3 plus. Those are the only oxidation states we particularly care about. Those are the only oxidation states that are stable for those elements. So we can have 2 plus and 3 plus on the tetrahedral sites, and we can have 2 plus and 3 plus on the octahedral sites. Okay, now the 4 end members then, here we have A2 plus B3 plus 2 in this corner. That's your normal spinel, your hypothetical normal spinel. In this corner we have A2 plus 2O4, 2 minus, this is a hypothetical charged compound. Over here we have another hypothetical charged compound, and here's a third hypothetical charged compound. These are your 4 end members by taking one from this lattice and one from this lattice. Okay, now clearly the charge of the actual material has to be neutral, so you have to go along a line in this system in which the total charge is 0, and this is your neutral line along here, which takes you from this corner up to, and this is your inverse spinel. Your inverse spinel, your hypothetical inverse spinel is not an end member. The hypothetical inverse spinel is this point here, because in the hypothetical inverse spinel you've got B3 plus on the tetrahedral sites, and A2 plus and B3 plus are randomly mixed on the octahedral sites, and this is your neutral line. So here these are the site fractions, which I've called little y and z, and along the neutral line, z equals y over 2. Now, as I said yesterday in FactSage, when you're running FactSage, this will be taken care of. The neutral line will be taken care of, because when you enter the end members, you're entering the Gibbs energies of the 4 end members. You enter the end member stoichiometry, and you give it a charge. So you tell it that this is A3O4 2 minus, this is B3O4 plus 1, and so on. So each of these things has a charge. And this has a charge. This has the electron becomes an element. You don't enter it as an element, you just enter the charge, but internally it's like it's another element. So this has 2 electrons, this has 1 electron, this has minus 1 electron, this has 0 electrons, and since your total number of electrons that you enter is 0, it keeps you along that line. Okay, so the Gibbs energy of the mixed spinel then, look, I've called these just for simplification. This is the G naught of this end member is G naught 1, this is G naught 3, 4, G naught 2. So it's the product of the site fractions. Z is y over 2. Okay, so the G naught 1 is multiplied by y times C. G naught 1. Look up this one. I think I may have the numbers wrong here. yz times G naught 2, that's okay. This is yz, y times z times G naught 2, y times 1 minus z, it should be G naught 4, shouldn't it? 1 minus y times 1 minus z for G naught 3, that's okay. And 1 minus y times z for G naught 4. Oh, that's backwards. Right, you see this should be G naught 4 should be, it doesn't matter. G naught 4 here should be y times 1 minus z. G naught 4. Yeah, I've got these numbers backwards, so inverted the 1 and the 4, so they should be backwards. This should be G naught 4 here. So G naught 4 is 1 minus y over 2 is 1 minus z. So this is y times 1 minus z, G naught 4, and this should be G naught 1. So change the 4 and the 1 here. Then you have your ideal mixing term, which is RT, well, and I'm not putting in these L terms. The second nearest neighbor interaction, these alpha terms or the L terms, I'm not including here. I'm dealing only just with the G naughts to give you an idea. Now, model parameter is the site exchange energy. So this is going from normal to, and so okay, the actual, this is actually a one component system, well, not exactly. You're somewhere along this neutral line here. We're somewhere between this AB304 and this point over here. So the actual real compound lies somewhere on this line. The real mixed spinel is going to be somewhere here. Where it is on this line depends on the Gibbs energy change for this site exchange reaction. If this site exchange reaction is strongly shifted to the left, then the equilibrium point here is shifted towards this corner. And if this is very negative and it's shifted to the right, then you're shifted towards the inverse spinel. Okay, but the actual system, not only does the actual system lie only on this neutral line, it only lies at one point on this line. This is a one-component system. This is an internal equilibrium we're talking about here, not equilibrium with other phases. It's an internal equilibrium within the phase itself. So we're trying to come up, really we're getting a whole big model here with 4 end members and everything in order to model a single component of what AB204. The real AB204. You cannot, in reality, you cannot be anywhere you want in this line. You're only at the internal equilibrium point. You can't control this. You can only do something. Okay, I'm going to make a really simple model. You can make the model more complicated, but let's call these the epsilons, call these the site energies. C, let's say that these are the energies of an ion on that site. So epsilon A2 plus is the energy of an ion on the tetrahedral site. Epsilon A2 plus is the energy of an A2 plus ion on an octahedral site. And we're going to have, we basically have 4 n-member Gibbs energies. We find that we're only going to need, these can all be set equal to the same number. We only need 2. There are only really 2 actual constants in this system. So we can set all 3 of these equal to the same thing without any loss of generality. You'll see in a minute what I mean. So we arbitrarily let all these equal C. And therefore G01 then, the one that's independent, so G0, so in the simple model then we say G01 put the numbers on there wrong. What did I get? I gotta read these things over. This is actually G03. Okay, G03 then is the energy. G03 has an A on the tetrahedral and 2 B's on the octahedral site. So we'll say the Gibbs energy of 3, I got the numbers all wrong on here. G03 is the energy of the A2 plus on the tetrahedral site plus twice the energy of B3 plus on the octahedral site. And so on. This, the G04 is epsilon of A2 plus tetrahedral plus twice the epsilon of A2 plus octahedral. You imagine you have the site, you got energies of putting the things on the site. So this is an extremely simplified model. We're simply saying that every G0 is simply the sum of putting that ion into, that's the lattice energy of putting this thing in. So if you have an epsilon on this A2 plus of the tetrahedral site and 2 B3 pluses on the octahedral site, that gives you the G0 of, should be 3, and so on for the other things. Then, if you put all this together, you make this substitution for your various so these are your G naughts. Each of your G naughts can be expressed as the sum of a couple of these epsilons. There are actually 4 epsilons, and there's an epsilon of A2 plus on the tetrahedral, epsilon of B3 plus on the tetrahedral, and so on. So each of these n members can be expressed as a sum of 2 G naughts, can be expressed as a sum of 2 epsilons. We let these 3 epsilons be the same arbitrarily. C will become a parameter of the model. We make these substitutions back into equation 1, and you end up with this, assuming that I haven't screwed up all the G01s, G02s, and G03s. I'm sorry about that. And we end up with this equation. Okay, now 1 minus y times 1 minus y over 2. Well, let's just look at that. 3c, if I've got this right. I'm all screwed up. I should really redo this. Okay, I do have this one right, okay. 1 minus y times 1 minus y over 2. Yeah.
In this, you made y and g with that's right, the equation is.
I should maybe go back and do this whole damn thing again. What do I... And I do what here?
Y and g the same.
Where do you get this from?
This is the correct one. Sir? No, it was in the circle.
This is what's on the site? No, I had her put up, I corrected these things. And I... So I rewrote it. This is rewritten. Well, this is different. I changed this the other day, and I asked Ev to put this new version up on the... When did you print this out? Just recently?
No.
A long time ago.
Just 1 month ago.
Oh, okay. I modified it here. Sorry. You know what I should do, because this is just wasting time. Why don't we take a 5-minute break? I'm going to correct this, and then I'll show you how it has to be corrected. Okay? That's taking this. Take a break. I don't know what I did. Where did I get these numbers? I had the numbers right on this one. I screwed them up on this one. Then. 3, 1, 2. All right. I don't know. I thought I had it all right. Okay. Sorry about that. I thought I corrected this all. This is supposed to be the right one, and I made a mistake even here. All right, this should be G naught. Okay, we'll leave it that way. Then this should be G naught 4. If I haven't made another mistake here by going so fast, I'll look at it this afternoon and I'll make a correction next week. But anyway, the point is this should be G naught 4, this should be G naught 1. Okay. I've arbitrarily set this to be the site exchange energy, so the delta G, therefore your delta G of your site exchange should then be epsilon of A2 plus on the octahedral plus epsilon of B3 plus on the tetrahedral minus epsilon of A2 plus on the tetrahedral minus epsilon of B3 plus on the octahedral. Okay, so there's your site exchange energy, which is the difference of the energies, the lattice energies of those ions on the sites. And we're going to arbitrarily set these three to be equal to a constant. Okay, and then the Gibbs energies, then G naught 1, then G naught 1 has 1 is this. This should be G naught 3 here. Okay, this should be G naught 3. And that's the epsilon, so G naught 3 has an A on the tetrahedral and 2 B's on the octahedral. So it's epsilon of A tetrahedral plus 2 times epsilon B of the octahedral, and you do the same thing for the other corners. This would be epsilon of A2 plus tetrahedral plus twice epsilon of B3 plus, and so on. Okay, so now we go down to here. So we have 1 minus y, let's take the first term, 1 minus y times 1 minus y over 2. That multiplies g naught 3. 1 minus y times 1 minus y over 2 multiplies g naught 3. G naught 3 is epsilon of A2 plus tetrahedral plus 2 epsilon B3 plus octahedral. Both of those are equal to C. A2 plus tetrahedral, B3 plus octahedral, I arbitrarily set them both equal to C. So this then G naught 1 is equal to 3, or G naught 3 is equal to 3 times C. Okay, so we have 1 minus y times 1 minus 2 times 3c. And similarly, this corner here, G naught 4 is the epsilon of this plus twice the epsilon of this, and they're both also equal to c. So G naught 4 is multiplied by 1 minus y, y over 2. 1 minus y times y over 2. That's G naught 1, because I changed it. 1 minus y times y over 2. This is... Okay, this should be 1 minus y times 1 minus y over 2 here. 1 minus y times 1 minus y over 2. And that's going to be again multiplied by 3c. No, it isn't. Now I got it. This should be y times 1 minus y over 2. Make it 1 minus y over 2, y. 1 minus y over 2, y is this one, 1y times 1 minus y over 2, that's G naught 4, and that is equal to this plus twice this, which is again 3c. Okay, so you just got to work these out. This should be y times 1 minus y over 2 times 3c. This one is okay, and this one should be 1 minus y times y over 2. I'll make this up again and I'll put it up on the web, on the server correctly, okay? But you get the point, you're multiplying this together. Now, these other ones here, y times y over 2, y times y over 2 multiplies this corner, which is tetrahedral B3 plus, so 1 times B3 plus tetrahedral, 2A plus octahedral. Okay, they're not both in here, but then by mixing and taking the site to exchange energy, combining it with this, okay, you can work out this then, this y, okay. Y times y over 2 multiplies this. Okay, and G naught 2 then, G naught 2 should be epsilon B3 plus on the tetrahedral plus twice epsilon A2 plus on the octahedral. That's G naught 2. Which is this corner. G naught 2 is equal to B3 plus octahedral 2 times A2 plus octahedral, multiplies y times y over 2, and taking this together with this delta G site exchange, you can work out that comes out to delta G site exchange. This then is equal to delta G of the site exchange plus 3c. You work it out. And the other corner is the same. So I will check to be sure that I've got all the numbers right, but that's the idea. So you have two of these are, so dg dy equals 0, and z is just y over 2. Now, FactSage just takes it from here and minimizes the Gibbs energy for you, but to see what's happening internally, the minimum Gibbs energy, the actual point where you are on here, is given by setting dj as 0. And when you work that out, this of course always gives you an equilibrium constant. Okay, so you'll see that the equilibrium constant, and you'll see now what we're finding out is the following then, that the equilibrium constant The equilibrium constant depends only on the delta G of the site exchange energy. It doesn't depend on C at all. Okay, there's only one constant which is determining where you are on that line. Okay, and this is y squared over 1 minus y times 2y. If the site exchange energy is very negative, then you tend to have this tends to be quite large, okay, and that then shifts the site exchange energy is negative, you're shifted to this side, A2 plus in the octahedral, the way I wrote the site exchange energy here, okay, and you end up shifting towards one end or the other depending on which way you go. Okay, you solve for y then to get the degree of inversion. So if y is very small, you're going to be down here. If y is very large, you're going to be. Okay, so if the site exchange energy is negative, y becomes large. If the site exchange energy is negative, then you see y is large. The site exchange energy is negative means you get shifted towards the inverse side, and that's what's happening. If delta G exchange is very positive, y is very small, and you get shifted back towards that side. Okay, so you're solving this for y. It tells you where you are on this line in the real spinel. And this is done internally then by faxing. Okay, so where is this other constant C comes in? Okay, well C then determines the Gibbs energy of the entire thing. Once we have the value of y, we know the value of y, we substitute the value of y back into this expression here. We have the site exchange energy, we have the value of y, the equilibrium value of y, substitute that all back into this expression, and you get an expression for G as a function of the parameter C. This then is the Gibbs energy of the real mixed spinel, which you can get out of the thermodynamic table. Okay, so then the constant C is adjusted in order to make the Gibbs energy of the system equal to the Gibbs energy of real Fe3O4. So you see you really have two parameters. You have the C parameter. Remember, this G03 is not the Gibbs energy of Fe3O4, real Fe3O4. That's your hypothetical normal. This is your hypothetical inverse. The real mixed spinel is somewhere in here. So the y, the delta G site exchange determines the value of the parameter y, which puts you on this line, which also is z. Once you've got that point, then you know where you are, then you can go back and find out the constant C, which is related then to the Gibbs energy of the real spinel, and you adjust the two. So you really have two parameters. You have a C, which is related to the Gibbs energy of the one component system, and then you have the delta G site exchange, which sets you on your internal equilibrium. Okay, now you don't have to set these. You could do the same thing. You could arbitrarily set all three of these equal to the same number, or you could set this equal to 3 times that and that 2 times that. It doesn't matter. 3 of them are arbitrary, basically, and the fourth one is what's due. If you work it out, you see that it doesn't really matter what you assume. You're still going to end up with 2 parameters. I just did this as one simple way of doing it. Now this oversimplifies things because you have the second nearest neighbor site exchange energies, which you can take into account with those alpha, the L parameters, and so on, and then you end up with other. So the whole thing can become quite complicated. This is kind of just assuming that the G naughts are the sum of site energies is also an oversimplification, but it gives you an idea of what we're dealing with here. Now, if you want to look into this more carefully, you can read the papers on the spinels and so on. But this gives, for every different kind of mixed ceramic, if you're dealing with perovskites or olivines or whatever, when you have equilibrium between 2 sublattices, it's the same general idea. So that's a very simple case of AB204, telling you where you are in the line. If you had Fe3O4, you would have the same thing. Fe2 plus and 3 plus would be the A's and B's. And of course now you can put more and more ions, A, B, C, D, E, on the different sites, and you get the whole thing can be worked out. But you must be very careful, as we showed. This would take me a long time to go through this, the details, and every ceramic's a little bit different. But Sergei showed a few interesting cases as well, where if you can take a simple system like AB204, and you can make different assumptions. He found that, for example, he took, I think, AB204, and what he did was he sort of found out where you were on this line, not by fixing the G's, but by fixing these L parameters, the second nearest neighbor parameters. And he showed that actually you could end up with exactly the same mathematical expression as this in this Fe3O4 system, but it's not the same when you go up to the multi-component systems. Okay, so assuming, you can make assumptions that some of these things are caused, say, by the second nearest neighbor parameters, and you can actually end up with a mathematical expression that is identical, but it's not identical in the multi-component system, and because it's physically unreasonable. So which one is physically reasonable? This is more physically reasonable to assume that it's the site energies rather than that it's some sort of a second nearest neighbor bond energies. Okay, but they say, oh, it's the same mathematical expression, it doesn't matter. Well, yes, it does matter, because in the multi-component system, it's not the same mathematical expression. So anyway, in this course, I can't go into all this. Is a whole subject in itself, is how you treat these ceramic systems, but I'm trying to show you how the thing works, what it means to have charged compounds, and to repeat for the 50th time, the most important thing is to think about what the actual physical model is before you just go and start choosing parameters at random. You can't just randomly choose parameters to fit it. You have to really think about what the model parameters are and what physically you're dealing with. Okay. So that was the introduction to ceramics. Are you going to be dealing with anybody in your group dealing with ceramic systems a lot? I guess you're doing the oxides, you're going to be fiddling with these things. Okay, this is going to be your most difficult task, is when you start to get these big systems, perovskites, spinels, olivines. They have big ranges of stoichiometry. Okay, this is where the challenge is going to lie. So, any questions about the general concept of this thing? Now, it would be nice if we could have, remember, we're only doing this with the compound energy formalism with no short range order. If you wanted to put in the short range order, you could always add this big lambda parameter, the Taylor expansion term, the x1, x2, x3, x4. I think we should be adding those. We aren't. The thing is, in these ceramic systems, it's interesting that all the energies of these, the reason that these systems have such broad ranges of solubility, that you can put all sorts of ions here and all sorts of ions here, is that these energy terms we're dealing with, the delta G sites exchange and so on, are not terribly large. Okay? And the reason for this is that really when we talk about first nearest neighbors and second nearest neighbors, as I said earlier, we're thinking about these two sublattices, and we say, okay, an A2 plus here, an A2 plus here, and the V3 plus here are nearest neighbors. But they really aren't. They're separated by another lattice, the oxygen lattice, which we're ignoring. So they're already shielded. I mean, you have an A2 plus here, then you have an oxygen ion, then you have your V3 plus over here. Okay, so this interaction, they're quite far apart. They're shielded by the oxygen ion here, so the interactions are not strong. It's not like interactions in, say, a molten salt where the sodium and chlorine are right next to each other. They're separated. It's even a bit further when you're talking about two ions on the same sublattice. So the interactions are not as strong as they are. So since the site exchange energies are not all terribly that strong, you tend not to be shifted all the way one way or all the way to the other. Everything tends to be mixed up. Everything goes on all the, which makes for more of a challenge for optimization. The big challenge in optimizing these oxide systems is not really the liquid phase as it is in some others. It's real, or it's these extended solid solutions that you get. Okay. When you mix sodium oxide, aluminum, silica, the liquid model is complicated, but you have all sorts of solid solutions, all of which have these different sublattices, and everything can go on the sublattices. You've got to be sure you've got a reasonable model, or else it won't go into other systems. And this is really the challenge, is when you get into these extended solid phases. If you have an oxide system that has a liquid phase, but most of the compounds are stoichiometric compounds like calcium, aluminum, silica, you have just line compounds, not a lot of big solid solutions. And it's relatively simple. I say relatively. Then you get to these systems with big solid solutions, and it's no longer simple. But this is the approach you have to do. It's the theory behind it. Okay. Now I want to go to molten salts. Back to molten salts, and that will then lead us into slags, which are liquid oxides, liquid silicates, which are really molten salts, molten ionic materials. molten salts and slags generally. People talk about slags as they're different, but they're ionic liquids, so molten salt, slag is the same thing. So this was this file number 25, which I showed you earlier. And there I talked about systems. Let's take, there are many systems here were similar. Let's take the system of alkali chloride, cobalt chlorides. These were the different alkali chloride, cobalt chloride systems. This parameter, the lambda, but this is the heat of mixing over x1, x2. It just tends to, as I said before, emphasize the minimum. In a system like this, in a system like, say, potassium chloride, cobalt chloride, we're talking about liquid phase here, completely miscible. The heat of mixing in this system is a very strong negative peak at about 33%, which is the K2CO Cl4 composition. Strong negative peak. Here in this graph here, we simply plotted this. Just okay, you get a strong negative peak, indicating that you have short range ordering at 33%. Okay, like 2 lines as we said before. Suggests the quasi-chemical model, of course. This is simply the heat of mixing divided by x1, x2, and it just emphasizes it. It exaggerates makes the peak even more exaggerated. In other words, if this was a regular solution, if you had a regular solution, then the heat of mixing would be x1, x2, and so delta H over x1, x2 would be a constant. So in a regular solution, this thing would be a straight line across here. The fact that it dips down at around 33% just emphasizes the fact that you've got a peak here. You see with the lithium chloride, it is pretty close to being, it's just solid lines you want, the dark lines. The others were various models we were looking at in this paper. The solid line is almost, that's almost a subregular model. Then as you add sodium, potassium, rubidium, cesium, it gets more and more pointed. So basically if you have lithium, if you plotted the heat of mixing, the lithium chloride is going to be more or less regular. Sodium chloride, potassium chloride, rubidium chloride, cesium chloride, and the lithium chloride, the minimum is around 50% from here, and then you see the minimum shifting and moving a little bit further. The cesium minimum is almost exactly 33. As you go up to the sodium minimum, it's a little bit more towards it. Okay, so definitely indicates strong short range ordering at 33%. And the entropies have been measured as well. The entropy of mixing it is the same thing. You've got an entropy of mixing that looks like this with a minimum around 33%. That would be in the cesium system. Then as you go to rubidium, it's less marked. Potassium, the sodium, and the lithium would be almost an ideal solution. So again, a more negative entropy peak at 33, shifting over towards the ideal mixing for the lithium. I don't actually show an entropy peak here, but this is actually measured. These are entropies. This was in this cobalt and magnesium. This was the partial entropy of alkali chloride. Okay, the partial entropy of alkali chloride. If your entropy curve looks like this, and this is your alkali chloride, then this point here is the partial entropy of ACl. So you imagine this tangent rotating around here. This point here goes up, and then it comes back down, goes up again. Okay, so you see that's what happens with the cesium. The partial entropy of ACl goes up, then comes way back down, and then back up again. With rubidium, it's less pronounced. Potassium, sodium, lithium, it's hardly. All right, so we have some sort of a short-range ordering around 33% of cobalt chloride or magnesium chloride, which is weaker with lithium chloride and gets stronger as you go down to cesium. And we find that this is all sorts of salts in which you have alkali chloride with MCl2, where M is a divalent ion. You get the same sort of thing. So here we got these were the series with cobalt. Here we have the series with iron and nickel. Same thing with the iron over here in the alkali chlorides. This is iron with nickel chloride, same general idea. Here we have the thing with manganese chloride, alkali manganese chloride, same trends, 33%. magnesium chloride, cadmium chloride. There we just had 2. Lithium and cesium, we didn't have measurements for the others, but they'd be in between somewhere. Although we see here, this tends to be a bit less pronounced. If you look at the cesium here, it's less pronounced than the cesium here. Lead, again, same thing, but the lead is not as ordered. Obviously, the lead is ordered with cesium around 33%, but the ordering is not as strong as it is with the... Okay, so they're all the same, but the divalent cation has some effect. In case lead is not as ordered as, say, magnesium or cobalt. It does not have to be chlorides. Here's the fluoride, lithium. This is the lithium fluoride, beryllium fluoride, potassium fluoride, beryllium fluoride, rubidium, same idea. And we showed that's with magnesium and manganese. Just about any divalent cation comes out to be the same sort of thing. Okay, so how do we explain the short-range ordering? Well, we talked last week, we did the short-range ordering in which we talked about complex ions. Okay, so we take the system KCl, MgCl2, and we have K+, and over here we have chlorine and MgCl4. And that's clearly giving you short-range ordering around MgCl4 composition. Because when you get to K2MgCl4, the K2MgCl4 compound is K2+, K+, MgCl4. It's a completely ordered compound. So if you use this model here, and you looked at the entropy of mixing going from KCl to K2MgCl4, it's going to go like this, with a 0 entropy here. Sorry, MgCl2. The entropy is going to go like this and go back down to 0 at K2MgCl4, which is a completely ordered compound. So you're going to get this side. This model with the complexes only applies on this side. You can't. This model doesn't tell you anything over what happens over here. But it does seem to work rather nicely over on this side. And it's going to give you a strong negative heat of mixing as well. Your heat of mixing, if you take the heat of mixing between KCl and MgCl2, what it's going to give you is it's going to give you a strong heat of mixing down here to 33%. Why? Because this then is basically, this heat here is the enthalpy of forming this compound. Okay, what you're doing is you're taking KCl, when you're mixing, this is the delta H of mixing, KCl plus MgCl2 produces the solution. Okay, so here you have KCl, 2 KCl, 1 MgCl2 produces the solution. Here you're basically, it's the energy of forming these complexes is what you're getting. It's not over here, of course, the model doesn't tell you anything. So it's giving you a very negative heat. The heat would be the energy to form that compound. So this model with the complex ions works well on the left-hand side. Okay, it will give you the entropy goes this way, it'll give you a strong negative heat coming down. But it doesn't explain what goes on the other side, and clearly something goes on the other side. Okay, so your complex model is very simple, and it's nice for simple calculations as we were doing, but only on the basic side, the left-hand side. Now, this now suggests here, of course, that we're going to use the quasi-chemical model. So the modified quasi-chemical model. And how would we do the modified quasi-chemical model if we were mixing alkali chloride and some, let's say, cobalt chloride? So I'm going to mix KCl and COCl2. Okay, now you have the metals. So I'm going to model this with potassium and cobalt. Forgetting no complex ions now. Potassium and cobalt going to be modeled like this. Potassium and cobalt ions on the cation lattice, and chlorine ions on the anion lattice. But these are not randomly mixed. They're strongly short-range ordered. We're going to use the modified quasi-chemical model. So we're forgetting this lattice. We're really only dealing with this lattice here. Okay, so it's really a one sublattice model because we can just forget this. When I'm talking about pairs, I'm talking about cation, second years neighbor pairs. And so now we have the KK plus cobalt, produces 2K cobalt. Second, these are nearest neighbor pair. You can put pluses on here. Okay, so we're going to apply the one sublattice quasi-chemical model to this system. With all these sites occupied by chlorine, we're simply considering potassium and cobalt mixing on their lattice sites. And there's going to be a delta G for this reaction, the parameter, which is going to be quite negative, indicating that the potassium and cobalt prefer to be second nearest neighbors. They prefer to be second nearest neighbors on their lattice sites. So clearly then, if we take delta G as 0, we apply the one sublattice quasi-chemical model. We treat the system just as we were treating the system AB before, with AA plus BB forms 2AB, the simple one sublattice quasi-chemical model. And clearly then, we have the Z, so we would have Z of cobalt 2 plus equals 2 times the Z of potassium plus. Sorry. Z of potassium, 2 times Z of cobalt. That puts your minimum at 33%. Okay, so your maximum ordering is then going to be at K2COCl4 composition. That's going to be your maximal composition where the coordination number of cobalt is twice the equivalent. Okay, so we apply the simple sublattice model. This is if we were doing a system like nickel sulfur liquid or something, in which we have a minimum. We have a minimum of 33%. Simple one-dimensional model with a delta G for the site exchange reaction set negative. Z of potassium is 2 times Z of cobalt, so that the minimum is shifted to 33%. And as we make this delta G more and more negative, we're going to get a more and more negative peak and the entropy, so we can fit the system. Okay, so mathematically the system can be fitted using the modified quasi-chemical on the one sublattice. Okay, but how does this relate now to the, does this relate to reality? Because we really seem to have evidence in these systems for these complex ions. If you go over, at least on this side, certainly systems such as nickel, you can have, in water, you can have NiCl4 complex anions in water. Nickel chloride complex, NiCl4. 2- complex anions in water. We can take spectra of those ions. We can compare those to the spectrum of these molten salts in this area, and we find that the vibrational frequencies tend to be quite similar, which would indicate that the nickels really are surrounded by 4 chlorines and they're kind of going together as kind of a unit. So this kind of is indication that we have NiCl4 complex anions, and also the complex anion model is a very simple model. It works quite nicely over here. So how do we, is this just mathematics and it doesn't really relate to reality, or how does this relate to the complex ion model? I maintain that the two are just two ways of treating the same thing. So what we're saying here in the quasi-chemical model is we're saying that cobalt prefers nickel as second nearest neighbors. Okay, and the ratio is at the 2 to 1. So let us imagine that we have a cobalt ion here, and the cobalt ion has 4 chlorines. I'm not going to write chlorine, I'm just going to write a negative. Okay, so the cobalt ion is surrounded tetrahedrally by 4 chlorines. Okay, that's its first coordination shell. And then around it, in the second coordination shell, you have potassium ions. Preferentially in the second coordination shell, you have potassium ions, single pluses, because in the quasi-chemical model, the cobalt-potassium second nearest neighbors are favored over cobalt-cobalt. So you'll have a central cobalt, then the next shell is chlorines, the next shell then is mainly potassium ions. Okay. That's what the quasi-chemical model gives you. But you see now that this central thing, if you consider this cobalt with the 4 chlorines, that's like a complex ion. Okay, the cobalt has its 4 chlorines around it. If you take a vibrational spectrum of this, you will find the cobalt looking like a complex ion. But formally, mathematically, saying that the cobalt and the potassium are preferential second nearest neighbors is basically saying that a cobalt with its 4 chlorines is going to be surrounded by potassiums and therefore is acting more or less like a complex ion. Okay, so this does not say that there are not complex ions, it just says that in the mathematical treatment it's better to treat it this way than by the complex ion treatment. The reason being that complex ion treatment only works over to 33%, and even then it doesn't go all the way to 33% because it would predict the heat going, and the entropy going to 0 when it tends to round off. So on the other side then, so this quasi-chemical model applies across the whole thing. But when the delta G is quite negative, you do end up with something that means that every cobalt in its second shell is going to have potassium, so it looks like a complex ion. So 2 models in the basic end then, where there are not very many of these cobalt 4 minus cobalt Cl4 species, you can see that you can actually then in the modeling you could treat this as a separate ion, since the cobalt with its 4 chlorines, if you treated this in the basic end, if you treated it as potassium, chlorine, CoCl4, obviously every cobalt chloride complex is going to be surrounded by potassium. That's what we're saying here. But here we're saying it has to be completely surrounded by potassium. That's also, this model is limited in the sense that this complex ion model is limited to, it's limited to the 33%, but it's also limited because even in this region over here, it's not going to be completely complex. Like not every cobalt is going to be surrounded. There could be cobalts over here as well in the real situation, and this is certainly the case when you're putting, say, lithium in, which the thing is tending much more towards an ideal solution. This complex model doesn't permit that. The complex model says every CoCl4 is clearly only surrounded by potassium. It assumes basically complete shifting. Doesn't matter what. Okay, you can't shift the reaction back to the left because obviously in lithium it's not that highly complex. It's always completely complex. It's like the modified quasi-chemical model with the parameter completely shifted to the right. It's an extreme model. Okay, this quasi-chemical model permits things to be shifted. So when you have your KK plus cobalt produces 2K cobalt is shifted very strongly to the right, then you end up with basically this. But in sodium lithium it's shifted more to the left, so you have preferentially cobalt potassium or cobalt lithium first, or cobalt sodium first, second nearest neighbors, but you can also have some cobalt shift. And then clearly you can apply this on the other side over here as well. So over the other side you do have cobalt nearest neighbors necessarily, but there's still a preference for the cobalt to have the potassium in its second coordination. Okay, so I think the model is physically quite reasonable, and it basically, you can actually work the mathematics out yourself if you want. Take the quasi-chemical model in the quite basic region over here, make a very negative delta G so the cobalt's almost completely surrounded by potassiums, work out the equations for the Gibbs energy, write the equation then for the complex ion model, and the limiting case you'll find out they reduce to basically the same mathematical expression. So that's how we treat these systems. We treat them as using the quasi-chemical one sublattice model. Period. So there's really no difference from this and how we treated metallic systems, or say the system nickel sulfur, zinc sulfur, magnesium or aluminum calcium liquid, in which you have quite strong complexing. It's the same mathematical model, but we're dealing with the second sublattice, the cation sublattice specifically. So this is the type of second nearest neighbor ordering. As you recall back when I talked about the modified quasi-chemical model in the quadruplet approximation, I said if we had a system like KCl, MgCl2, KF, MgF2. Remember I said you have strong first nearest neighbor ordering, but you also have strong second nearest neighbor ordering. In the edge, members, this was when I talked about Eve's model and how you really have second nearest neighbor ordering, first nearest neighbor ordering. You can't treat the first and second nearest neighbor ordering simply by two separate pair models. We have in the quasi-chemical model for reciprocal systems, we have the ordering between first nearest neighbors, KCl, first nearest neighbor pair, plus magnesium fluoride, first nearest neighbor pair gives you potassium fluoride plus magnesium chloride. That's your first nearest neighbor ordering, which we, in the simple quasi-chemical model for this system, we can treat the first nearest neighbor short-range order. But now we have second nearest neighbor short-range order. We have potassium plus magnesium produces 2 potassium magnesium on the cation sublattice. So this is a second nearest neighbor ordering, which I'm talking about here, which applies along the binary system. And we needed the quadruplet model. Remember, in the quadruplet model, you deal with a quadruplet, which is A plus, B plus, X minus, Y minus. And then in the quadruplet, you can have first nearest neighbor pair ordering, you can have second nearest neighbor pair ordering. And you had to put the two together. They're coupled. And the second nearest neighbor ordering, as you can see, can be quite strong in many systems. And the second nearest neighbor short-range ordering can't be ignored in many of these systems. Okay, anyway, that aside, this is the way we treat these binary systems using the modified quasi-chemical model with ordering on the cation sublattice. Ordering on the anion sublattice is seldom, if ever, necessary. If you go between KF and KCl, it's almost a random mixture. Okay, let's take a break, and then we're going to talk about trying to systematize some of these molten salts. This will be straight chemistry. No, that's not what you do. Do this. There you go.